Okay, so this lesson is called Dapps2, and it is about the topic of related rates. So that means if there's one quantity that's changing and we know the rate of change of that quantity, and there's another quantity that's related to the first one, what would be the rate of change of that, right? So let's jump right into it with this first example. So here we have that let A be the area of a circle with radius r, and suppose the circle expands as time passes, right? So this happens all the time, whether it's a ripple because you dropped a stone in a pond, that's an expanding circle, or you spill something on the ground and that is going to be an expanding circle, or a raindrop falls and it starts to make a circle. Whatever the case may be, we have a circle and we are told that it's expanding with time. So there's a radius which is changing, so the radius is a function of time, and there's also the area of the circle, so the area is also a function of time. So when we talk about the related rates, these two rates are going to be related, right? So you may know the rate at which the radius is changing, dr dt. You might know what that number is. Using that, we will be able to find dA dt. That's the basic idea, right? So in this particular problem, the area and the radius are related by the circle formula A is equal to pi r squared. Now remember, in these related rates problems, right, we're always taking the derivative with respect to time, right? So the functions are functions of time, r of t, a of t, and when you take a derivative, you're differentiating with respect to time. So we're doing d dt of both sides, right? So in this problem, I need to remember that. And so on the left, like we did in implicit differentiation, we're going to differentiate both sides. So on the left, I get dA dt. On the right, I would get pi, which is a number. And then let's think about r squared. R squared means it's this radius function, which is some equation in t squared, right? It's that radius equation squared. So if I'm going to differentiate it, then I need to have the chain rule, right? So just to give a specific example, when I say r of t, I mean, maybe it's 2t. Maybe that's the equation for the radius. Or maybe it's some other more complicated equation, but it is an equation with t in it. So then r squared means that equation squared. And so now I'm going to do a chain rule. My outside is the squaring, so it's going to give me a 2r. So outside is the squaring, inside is r. We treat the r as an inside function, very similar to implicit differentiation. So pi times 2r, and then the in prime, right, is dr dt, or r prime, right? So in prime is r prime. So we have to remember those things, and then we now have an equation that relates dA dt to dr dt for any specific radius, okay? So let's see how this would be applied in a problem. It says oil spills here in part B from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meters, right? So we have the same situation of a circle that's expanding, which we just talked about. So the area is pi r squared at any time. But remember, it's an area which is changing with time, and a radius also which is changing with time. So then we do exactly what we did in the first example, and we know that dA dt is equal to 2 pi r dr dt, okay? Notice that the rate of change of area depends on the radius, right? The radius here is r, and the dr dt is this other term on the right. So both of those are going to make your dA dt be bigger. If you have a big circle and it's expanding at this constant rate of 1 meter per second, then you're going to get a bigger area change. if the dr dt were higher, I mean, they gave it to us here as 1 meter per second, but obviously if it was 10 meters per second, then the area would be going faster as well, growing faster as well. Okay, so in this question, they just asked us how fast is the area changing when the radius is 30 meters. So we just take our equation here, dA dt, and we put in 30 for r, 2 pi times 30. The dr dt is the given rate, which is 1 meter per second, and so we get the answer of 60 pi. Now notice that the units all work out because the 30 is in meters, the dr dt is in meters per second, and so my final answer is in meters squared per second, meters times meters on top. Sorry, no second squared on the bottom, just second, right? So this is the units of an area change, right? Change in area over change in time, which is what I would expect for a dA dt. Okay, so my answer is 60 pi, and the units is meters squared per second. Okay, our next example, example 2, says air is being pumped into a spherical balloon so that its volume is increasing at a rate of 100 centimeter cube per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So I have 6 steps that I recommend for getting a handle on these problems, and I'll try to do all of my examples using those 6 steps. The first step is to draw a picture and to label things, give things variable names, right? So picture plus variable names is the first step. So in this case, we're pumping air into a sphere, and we know we've got volume going on, right? So we've got V of this, so give it a name. I'm going to call my volume V, understanding that V is a function of time. It's changing with time. And then I'm seeing that they're talking about the radius, so I need an R variable, right? So my radius, it's also a function of time, right? So V and R are my volume and my radius, and I'm understanding the question. We're pumping air into this, volume is changing, radius is changing, the two rates are related. Okay, the second step is to identify the given rate. You will always be given one rate. In this problem, we're given that the volume is increasing at a rate of 100 centimeter cube per second, so dV dt is the given rate. Okay, third step is to identify the find rate. What are we being asked to find? Well, we are being asked to find how fast, there's your cue, how fast is the radius of the balloon changing. So we're being asked to find dr dt, and it's important to translate this correctly. When the diameter is 50 centimeters, you remember that with the Leibniz notation, we draw this long line, right? And we write down the place where we're evaluating the derivative at the bottom of the line. So when the diameter is 50, right, so d is equal to 50, then the radius at that time is 25. And I would want to make note of both of those things. So that's what we're asked to find. Okay, and so then the fourth step is to find an equation that relates the variables that you had in the first step, right? So in this case, I'm going to use the sphere volume, V is equal to 4/3 pi r cubed. That will usually be given to you if it's anything more than a circle. Circle, you're going to have to remember it's pi r squared, but any more complicated formula like that, it'll probably say it somewhere in the question. Recall that the volume of a sphere is 4/3 pi r cubed, right? So here's the volume, and now I just have to differentiate both sides, and that will be step 5, and you're going to do it with respect to time. So dV dt is equal to 4/3 pi is a constant. And let me think now about r cubed. When you're differentiating that with respect to time, it will become 3r squared, that's out prime of in, times in prime, which will be dr dt. So this becomes 4/3 pi times 3 times r squared times dr dt. You want to simplify this equation as far as possible at this step. So we get 4 pi r squared dr dt for our dV dt. Okay, that's step 5. And then in step 6, we will now go back into answering the question because we have to now put in the numbers, right? So step 6 is put in the numbers into, we basically have dv dt is equal to 4 pi r squared dr dt. I call step 6 the snapshot moment, right? Because the situation is changing all the time here. The balloon is expanding, the radius is changing, the volume is changing. We're being asked for dr dt at the moment when r is equal to 25, right? So this is what I mean by the snapshot moment, and you put that in at the last step. Do not put that in before, because the balloon is changing all the time. So we're only going to put in the r equals 25 at the very end when we're solving for the last answer. So dv dt is the given rate, and that was 100 the whole time. Dr dt is what we're trying to find, so this is what we're trying to find. And the 4 pi r squared, well, I'm at the snapshot moment now where the r is 25, so I will put in 25 for the r, and I will solve now for my dr dt when r is equal to 25. And so now, at this point, I want to remind you that sometimes, you don't want to do all the multiplication out. Some of these are going to be no calculator questions, and you're going to help yourself if you think like this. I have 100 divided by 4 pi times 25 times 25. 25 goes into 404 times, and then the 4's cancel as well, and my final answer is 1 over 25 pi, right? So at that last step, be clever about how you simplify without a calculator. So we have 1 divided by 25 pi centimeters per second for my dr dt. It's going to come out in the right units. If you want to double check that at this stage, you can think the 100 on the left is in centimeters cubed per second. The 4 pi has no units. The 25 is in centimeters, and you're squaring it. So now the dr dt is going to be in units of centimeter cubed per second divided by centimeter square. So 2 of these are going to cancel, and you're going to be left with centimeters per second for your final answer, right? So that's more of a physics sort of skill, but it's good here too to always provide units for your final answer. So 1 divided by 25 pi centimeters per second. Okay, so this is the basic idea. It's the same thing in every problem, but every problem is different, and there's no cookie cutter. You're going to have to think and apply the concepts to each different situation. So the next one says a cylindrical tank with radius 5 meters is being filled with water at a rate of 3 meter cubed per minute. How fast is the height of the water increasing? So my steps, again, first step is understand the problem, draw a picture, and put in variable names for the things that we're going to be interested in, which in this case, the question is talking about radius. That radius is not changing in the whole problem. It's 5 meters for the tank all the time, right? So you also want to think about what is changing and what is not changing. The radius of the tank is not changing. We're putting in water, right? So water height is another variable. I might call that h. And we also have been given a rate at which the tank is being filled. So the volume is another thing that's changing, right? So my 2 changing variables are v and h, and my thing that's not changing, you even actually don't want to give it a name. Things that are not changing, just write them in as numbers right at the beginning, right? So 5 is not changing, and that's the radius of the tank. Okay, so then the given rate is dv dt, which in this question it said is 3 meter cubed per minute. So just put that in, 3 meter cubed per minute. That's the given. The find is, what are we looking for? dh dt, right? How fast is the height changing? And I called my height h. And it says, it doesn't tell us when, right? So the reason might be sometimes the dh dt equation will be, it will not need a when, right? So it's just dh dt like that, okay? Okay, and then step 4, well, so for a cylinder, the volume is going to be equal to pi r squared of the cylinder, which in this case is 5 squared, that's not changing, times h, right? So in the equation, you only want to have the things that are changing, and those things you need to have them as variable names, right? So v is equal to pi 5 squared times h, or 25 pi h. And so then in step 5, dv dt is equal to 25 pi dh dt, okay? So now, step 6, we put in our numbers. dv dt is 3, and then we have 25 pi, and we're looking for dh dt. And notice there's no r's or h's or anything in the equation, right? That's why I didn't need a snapshot moment. I can just solve for dh dt. 3 divided by 25 pi, and this is going to be in meters per minute. It's a height, and the unit of time was minutes. Okay, our next problem says a person watches a rocket launch from a distance of 3 kilometers. The angle of elevation theta is increasing at a rate of 3 degrees per second at the instant when theta is equal to 45 degrees. How fast is the rocket climbing at that instant, right? So the picture, step 1, would look like this. There's a person here, this is the person, and well, they're standing above ground, but they're over there, and then there's a rocket over here. So the rocket is here and it's taking off, right? So the height of the rocket is changing, and the person is watching the rocket as it's going up. And so the angle of elevation means it's the angle at which you're looking up, right? That's changing, so we'll give it a variable name, theta. And h, the height of the rocket, is changing, so we'll give that a variable name, h. That's step 1. Step 2, identify the given rate. The given rate is here. The angle of elevation is increasing at a rate of 3 degrees per second, right? So d theta dt is equal to, not all the time 3 degrees per second. It is when theta is equal to 45 degrees. So when theta is equal to 45 degrees, at that moment, the angle of elevation is changing at 3 degrees per second. In calc, we always want to be in radians, so I'm going to change this information into radians. When theta is equal to pi over 4 radians, the angle of elevation is changing at the rate of pi over 60. That's if you convert 3 degrees into radians, you get pi over 60 radians per second, right? And radians don't have any units, so we just write pi over 60 seconds, right? Okay, then step 3 is the find rate. The find rate is, it says how fast is the rocket climbing, so dh dt, at that time, right, that instant, right? So we want the HDT at this same when, right? Remember, the long line tells us when, or the snapshot moment. So we want dh dt at theta is equal to pi over 4. Okay, so then step 4 is going to be to write our equation. So in this case, there would be no formula given to you, because you would need to realize, oh, I forgot one thing in my picture. I forgot to write in that the person is standing at a distance of 3 kilometers. That is something that is not changing, so I can put that here right into my picture as a number, and then I would have to notice that tangent theta is equal to h over 3. Or 1/3 h, right? Okay. So then we're going to differentiate both sides. Secant squared theta d theta dt is equal to 1/3 dh dt, okay? And now I just have to, oh, that was really step 5, right? And step 6, I have to answer my question putting in the snapshot numbers. Now, secant squared theta, remember, the snapshot is theta is equal to pi over 4. So secant of pi over 4 is rad 2, and secant squared of pi over 4 is therefore 2. And so 2 times d theta dt when theta is equal to pi over 4 is equal to 1/3 dh dt when theta is equal to pi over 4. D theta dt when theta is equal to pi over 4 is given to us, and it's pi over 60 seconds, right? So pi over 60 seconds. So going in here, I have 2 times pi over 60 is equal to 1/3 dh dt when theta is equal to pi over 4. This right here is what I've been asked to find, right? So I'm going to keep that on one side of the equation and solve for it. So dH dt when theta is equal to pi over 4 is equal to pi over 10. And that's going to be in kilometers per second, right? Let's check the dimensional analysis here. This side didn't have, it just had a seconds in the denominator, right? So this is like 1 over seconds. And then this 3 on the other side has, it's 3 kilometers, right? So basically this is going to come up here, and we get our final answer in pi over 10 kilometers per second would be the rate at which the rocket is rising at that particular instant. Our next problem is a very classic calculus type problem. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when, there's the snapshot, the bottom of the ladder is 6 feet from the wall, right? So read it a couple times, really understand the question before you start drawing your picture. The ladder is 10 feet long, so that's the slant height of the ladder. Here's the ladder, right? This is the ladder. It's 10 feet long. It's leaning against a wall, right? Here's the wall, okay? Okay, and then the bottom of the ladder is sliding away, right? So it must be looking like this in the next snapshot, and then like that in the next snapshot, because the bottom of the ladder is sliding away. The top is also moving down, right? The bottom is going this way, and the top is going down, right? And so they're asking how are basically those two, it's about those two related rates. It says how fast is the top sliding down when the bottom is 6 feet from the wall, and we also are given the rate at which the bottom is sliding away from the wall. That's 1 foot per second, okay? So let's kind of think about this again. I'm going to draw the picture again here like this, more mathematical-like, right? So I have 10 here, which is a fixed distance. It's not changing. The distance of the bottom from the wall, that's changing. And the distance of the top from the bottom from the floor, that's also changing. So those would be my two variables in this problem. That's step one. Step two would be given the given rate, right? So the given rate is that dx dt, the rate at which I'm sliding away from the wall, is 1 foot per second. Step three is what am I trying to find? I'm trying to find dy dt when, so that's the long line, when the bottom is 6 feet from the wall. So when x is equal to 6. X is my distance from the wall, the way I drew my picture. Okay, so then step four is going to be what equation is going to relate all this? This is going to be another one where you will not be told it's the Pythagoras equation, but you have to look at that and realize, yeah, this is a right-angled triangle, so at all times x squared plus y squared is equal to 10 squared. So that's your equation. Step 5, differentiate both sides, recognizing that x and y are inside functions, so 2x dx dt plus 2y dy dt is equal to 0. Derivative of 100 is 0. That's basically saying the ladder is not changing in length. Okay, then step 6 is our snapshot time, right? So at the snapshot moment, x is equal to 6, and dx dt is always 1 foot per second. So I can put the numbers in. 2 times 6 times 1 plus 2y dy dt is equal to 0, right? Now here's an example of a problem with an additional step, right? We need the y at the snapshot moment, right? Not, it's in general, it's changing, but this is at the snapshot. The x here of 6 is at the snapshot. We need the y at that snapshot moment, right? So you just have to think, well, if this is 10 and this is 6, this must be 8 by Pythagoras theorem. And so now we can put in 8 for the y. And we can solve, because I have now 12 plus 16 dy dt is equal to 0. So dy dt is equal to negative 12 over 16, which is negative 3 over 4. And this will be in feet per second. You can check the units for yourself.